and we looked through a couple of sort of simple examples of groups. So today, well, I mean, yeah, so yesterday we did the axioms, and we looked through a couple of sort of simple examples of groups. And today we're going, the outline is that we're going to, I mean, sort of before our break, we're going to try to cover two relatively simple groups, just a little bit more structure. We'll see structure in these examples sort of in the first half. And then in the second half, we will start, well, so the first one is permutation group. The second one is just like rotations in 2 dimensions, okay? So relatively simple and easy to visualize. And then after that, in the second half, we'll start on the 3D rotations groups, which start getting just a bit more complicated, okay? But I think, you know, we'll see elements just kind of building up as we work through some of these. Okay, so first of all, the permutation group, I mean, we're just going to do sort of 3 things, okay? So you're just going to have, you know, so you can imagine, say, if you had 3 balls, you know, identical balls, and I mean, you can't tell the difference between them, and, well, of course, I guess I didn't draw that very well, but anyway, yeah, so, you know, you can imagine that, you know, if you swap any of these balls, then you should still end up with basically indistinguishable configurations, okay? Now that's one way of thinking about permutations, and I guess, you know, if you were going to put some picture on this, you know, you can say, well, in slot, we have balls that are originally identified like this, and, you know, at the next step, so if this is the original configuration, then sort of after the transform, right, maybe this guy will stay the same, but these 2 will have gotten swapped, okay? Now, of course, the next step, if, you know, then you might, you know, swap around again. But of course, actually, from one transform to another, you can always just kind of relabel the slots, right? So, you know, in some ways, each one of the transformations can be characterized simply by these numbers. So this one, where you swap the second slot and the third slot, will simply be called 1, 3, 2. Okay? We'll just, you know, this will just be our labeling scheme. Now, of course, it's not just you know, identical balls that you might swap around. You can also think of these things as 3 amplitudes, okay, of, say, let's say, you know, going back to quantum mechanics, of degenerate states. Okay, so states of the same energy. There are 3 of them, and you can't actually tell the difference, which means, of course, that if you do a transformation and you sort of switch from one, or indeed oscillate from one state to another, it actually doesn't change the energy of the entire system. So in this case, then, you know, instead of thinking about, you know, sort of 3 slots, sort of, you know, physical slots where you put stuff, you'll just put like a complex amplitude in here. We'll say somewhat suggestive notation, actually, which we'll see a little bit later. So just 3 amplitudes, and let's say, you know, that's state 1, state 0, state -1. Okay, and if you're thinking L equals 1 angular momentum state, that is indeed where this picture is coming from. Okay, and the thing is that, you know, if you were to actually swap any of these amplitudes, then you have, I mean, you basically still have the same system. Okay, so that is the, you know, again, when we go back to symmetry, there are the things that you are transforming, and then the transformations which leave the system the same. Okay, right. So first of all, let us look at the group structure itself. Okay, so the group structure for a finite group is oftentimes written in terms of what we call a multiplication table, which is displayed up there because I really don't have the time to write all of that on the board. And you can see from the the elements, right? So E is going to be the identity element, which is simply, I guess, in this notation, right, it would simply be 1, 2, 3. Okay, but here I've called it E. And so if you were to take, say, this element sort of times this element, you will get the element inside here. Okay. So, right, yeah, E takes 1, 2, 3 to 1, 2, 3. So one thing that you notice immediately, just looking at this multiplication table, is that some of these terms, so let's say take these two here that are highlighted, right? This one, I think, is 231 times 213. This one is 213 times 231. So in other words, you've just switched the order of the transformations, and you actually end up with a different transformation as a result. Okay, so this is what we would call a non-abelian group. Okay. And I should mention, just before no, we'll keep on going with the structure here. Yeah. Okay. In the next slide, you will see the same multiplication table, but now I've just highlighted one quadrant of it, and that is because if you look at all the elements, so you have these three elements, and when you multiply simply by the same elements, you only get those elements back. Okay? So, in fact, these elements, right? So it's it's E, right? And then you have 2, 3, 1, and 3, 1, 2. Okay, so if you think about this in terms of where these original slots are, basically that's a cyclic permutation, and this one is simply a cyclic permutation in the other direction. Okay, so no surprise that these guys multiply among themselves, and when you have this, right, you have including. So now you have an identity element. Each of these elements has an inverse because you can always get from one of these guys back to the identity element. These guys actually form a group in themselves, and so that would be an example of a subgroup. Okay. Okay. Still, when I go to the next slide, still the same multiplication table. Now highlighting the off-diagonal quadrants. Let's see, now when I say that these things are self-contained, gosh, what did I mean by these things being self-contained? I actually don't remember. Anyway, you can, I think what I'm pointing out here is that if you get into one quadrant and then you apply the cyclic permutations, you stay sort of, say it more slowly. If you are among these three elements and then apply these guys, sort of as, multiply by these guys, you stay among these three elements, okay? And similarly, on the other side, if you're among these three elements, but then you had multiplied on the left side by these guys, then you'll stay among those three. Right. Now these are, so they're not cyclic. Also doesn't include an identity element. So these guys can't be groups in themselves. What you're seeing is that, let's see, these elements 2, 1, 3. So we have 2, 1, 3, and 1, 3, 2, and 3, 2, 1. Right? What are these guys doing? So put the 1, 2, 3s on top. And let's see, so these guys are being swapped, right? But this guy remains the same. In this case, you get a swap again. And here you have a swap going all the way across. Okay? So, yeah. So these are definitely outside of the cyclic permutations. You can't get these from here. But then on the other hand, once you've actually swapped them, you can still do cyclic permutations among them. Okay, so that's why you have these self-contained quadrants. Yeah. Now again, as I said, I mean, this is actually sort of foreshadowing some things that we will see in the groups that we come across later on. Okay, another thing that we noticed, not really so much about the multiplication table itself, is that if you wanted to start from one element and then get to all the other elements, or somehow kind of make up all the, I guess, what's the question would be sort of what's the minimum number of elements you need in order to multiply them and make all the other elements of the group? So yeah, it actually turns out that you only need the identity, you need to be able to permute, so do a cyclic permutation, and then you need to be able to swap. And a combination of these three elements, so just these three elements, you can get all the other group elements. Okay? And then, in that case, then these elements, which there are only 6, okay, so this is not really the most complicated example. You can say, well, if P stands for permutation and S stands for swap, then these would be this, you could actually replace all these numbers with these things instead, right, which are just a different way of expressing the group elements. Okay. These are sometimes what we would call, or this would be related to the concept of the generator. Okay, so a group element, which with successive multiplications you get to other group elements. Okay, I think that was it in terms of the structure of the permutation group. Okay, so we see a couple of these concepts that we will run into again. We have the subgroup. We have these sort of kind of self-contained quadrants. When you actually do sort of kind of like orthogonal transformations, and then you see the generators. Okay. Right. So as I said, we will bring these concepts back. Now now we're going to move to another group. Okay. Well, actually, any questions on the permutation group first? Okay. Now, obviously, people do permutation groups of higher orders, not just 3 elements, 4 elements, 5 elements, etc. And there's a whole field. Well, basically, there are people who wrote long dissertations on permutation groups. So you can really make quite a lot out of fairly simple elements. Okay, so right. Oh, I guess just one other thing that I'll point out about this is that, and you'll run into this in the written work if you haven't already. There is the. I've given you a couple different interpretations of the permutation group. Now, actually, it's not so much the interpretation of the permutation group. What I've actually given you is different possibilities in terms of what you're actually permuting, right? You can permute sort of physical objects. You can permute amplitudes, and in some sense, that's kind of the point of doing the group theory because the group doesn't really change. And all the mathematical things that you can say about the group, they don't really change just because you changed what you're actually permuting. Okay. That sort of gets into something that we call representations. Okay, because, right, you can think of the transformations as abstract operations. In this case, just, you can just kind of imagine moving things around. Or you can come up with some sort of concrete realization that makes it easier to think about these things, okay? So for instance, in this case, you can come up, especially since we have written a, sort of a state vector with 3 elements, you can write a matrix representation where, let's say, actually in that particular representation, you can say, well, here is the matrix, and we'll call it D132. So that's the element that the matrix will correspond to. I mean, this is the transformation that the matrix will correspond to. And because one stayed in the first slot stayed in the same place, we put a 1 there, and then the other ones get swapped, right? Okay? So, you can actually multiply that state vector by these kinds of things, and then that would sort of, actually do the mathematical operation of swapping the second and the third amplitudes. So oftentimes we will reduce things down to things like matrix representations just so that we can do the math. But of course, behind this, there's a more abstract operation that, it's kind of useful to keep in mind. This, by the way, is actually a little bit special because this is sort of taking the kind of the most naive basis for permutations. So sometimes this is called the regular representation. Okay? It's obviously not the only way that you can write down a representation because after all, who says that you only need 3 amplitudes, right? You just happen to be swapping 3 of them, but, maybe you're actually swapping, out of a whole bunch of, let's say 5 of them. Let's say you're only swapping these 3, right? In which case, you'll just have a bunch more zeros in there. I mean, they're different matrices. They're doing exactly the same thing. So it's a different representation, and it's a different space that you're operating on, a different space of state vectors, but it's actually the same group. Okay? So exactly the same algebra. Now, let's see. Now let's go to actually, before I go into that other group, I did want to just amplify on this concept of the representation. What you're actually looking for when we sort of make a mathematical representation is something that behaves in the same way. And now, what do I mean by behaving in the same way? So 2 groups. So rephrase this a little bit more mathematically. We want 2 groups with identical behavior. Okay. Now, what does that mean? It sort of means, I mean, given that we're talking about transformations, what we mean is that if you multiply 2 corresponding elements in one group, right, then let's say in the other one, which might be matrix multiplication or something like that, you have the corresponding multiplication, and the multiplication table ends up being exactly the same. So kind of an easy version of this, or the most direct version of this, is what we call an isomorphism. So this is, if you have 2 elements, say G1 and G2, which are elements of group G, and you had other elements H, corresponding elements H. Oh, I guess actually I have to have, forgot the third elements, right? Okay. Then G1 times G2 equals G3 will imply, or actually is true if and only if, H1 times H2 is equal to H3. Okay? I mean, this is basically what we mean by behave the same way. It has exactly the same multiplication table, corresponding elements multiply in exactly the same way. Okay? On top of that, you'll have a 1-to-1 correspondence between the elements, so like, G1 and H1, etc. Okay? So that's called an isomorphism, right? Every single element has its partner, and they all multiply in the same way. There's a more general concept, and in fact, most representations will not actually be isomorphic. They were what we would call homomorphic, which still sort of implies the same multiplication rule. Multiplication correspondence. But not necessarily one-to-one element-wise. Okay? So, just as a trivial example, so a trivial representation, so a trivial representation of almost any group, actually, is in fact that group with only one element, okay? Because, of course, if you mapped whatever group you wanted, and whatever group you had, and you mapped everything to the identity element, then clearly the multiplication rule is still the same, right? And every element corresponds, has a corresponding element in this guy. It just happens to be the same one. So you have the same multiplication rule. You don't have the one-to-one correspondence. So this is actually a trivial homomorphism. Trivial homomorphism. Okay. Now, shockingly, this will come up again. Okay. Now, let's talk a little bit about rotations in 2 dimensions. Well, at least just get started on this. Okay. So let's see. If you were talking about rotations in 2 dimensions, let's see. I guess. Well, first step is it a group? Okay, and basically you just go through the four axioms. Closure, right? 2 rotations, one after another is clearly equivalent of another rotation, so that one's fine. Associativity. Actually, this one, this one you can. If you just basically. This follows from the additivity of angles. Okay, because you are rotating through an angle. And then, of course, you have your identity element. So I guess I should be a little bit more concrete than this. So if you had, basically you're rotating through an angle phi, okay, and that's what you would be able to add and therefore get the associativity. Identity element is phi is equal to 0, and inverse is just going in the opposite direction, okay? So clearly this forms a group. Now, how many elements do you have? All right. How many elements? Anyone want to hazard a guess? Right, yeah, infinite elements, okay? Infinite number of elements, but it's not just sort of, it's not just sort of like any set of infinite elements. In fact, they are also continuously related to one another through a real parameter. Okay. Now, in this case, that real parameter is actually phi, which is the angle of rotation. Okay. So even though you have an infinite number of them, they are all sort of, connected. I mean, basically, yeah, they're all connected to each other. If they are close in phi, then they will actually be close, as a rotation as well. And this is actually well, actually, both of these things go into the definition of what we call a Lie group. Okay? So you've probably heard that term before. Now, let's see. What group are we actually talking about? The group that we are talking about is, in fact, SO2. So 2 by 2 orthogonal, or you might say that this is like a representation. Well, actually, this is a little bit of a problem in the way we do these things. Let's see, with determinant equal to +1, okay? Yeah. In the literature, you'll see SO2 being used for both the group of orthogonal transformations with determinant +1, or it will actually be the group of orthogonal matrices. Okay, you'll see both usages. Now, the nice thing is that it is actually an isomorphism between those two concepts, so you can kind of get away with this. And in some sense, the distinction is not really that critical. But some math papers which get really specific about this kind of stuff, they'll oftentimes use some sort of special font, which I have to admit is just going to take me forever to write. So I'm going to sort of skip that. Okay, and we'll just sort of take the isomorphism for what it is. Okay, let's see, going on. Okay, so we talked about the rotation. Of course, the rotation, has a particular form, which we can write down. So x cosine phi minus y sine phi. Y prime would be, x sine phi plus y cosine phi, which, of course, readily admits a matrix representation. Okay, and the state vector is, basically your coordinates. Yeah, and it's pretty obvious that take this and do the transpose and multiply it out, and you get +1. Okay, so. There is, as I said, there is an isomorphism between these matrices and rotations. And then let's talk about, just as the last little bit before we take a break, talk about the generator. Okay, now in this particular case, there is actually only one generator. So we can do this, first of all, you have this idea of the infinitesimal rotation. Okay, so we're going to rotate by some infinitesimal angle d phi. And we write it as 1, so the identity matrix minus I d phi times some matrix J. Okay, now this is a little bit conventional. Okay, there's no particular reason why it's plus I, or even, even having an I there. But I'm just going to stick with this kind of this convention. If you read in other textbooks, you actually have to go and look this up to make sure you know which convention the author is using, because it does change things a little bit. Okay, now if you do a whole bunch of these, right, you should be able to get back to a finite rotation. And the way that you do that, in fact, you use what is called an exponential map. Okay, so a finite rotation through phi would be equal to e to the minus I phi j. Okay? So actually, for the permutation group, I guess, we would have actually called this the generator because we were actually taking this element, this differential rotation, and then getting all the other rotations out of it, right, using the exponential map. But conventionally for Lie group generators, we actually use that term to refer to J. Okay, so a little bit confusing, a little bit unfortunate usage, but in any case, this is the one that you will see. Now, to get that particular rotation matrix, you will find that J is equal to 0 minus I, 0. So you can actually plug that into your exponential map and get the right rotation matrix. Yeah. Okay. Now, one thing that let's see. I guess no. Yeah. Something that you should note also, just in case there is any confusion about this, J, because of the definition, is not actually a member of SO2. Okay, just because yeah, sometimes just it comes as a little bit of a surprise that is the case, but it just RD theta, I mean RD phi is the thing that's actually an element of SO2, not J itself. Okay, now we're going to take that little break because right after that we're going to then start talking about the representations of this group. Now, because we are talking about group theory and highly abstract stuff, I figured, right, and you can put your pens down now, right? Figured, let's talk about experimental physics. I mean, serious experiment, and I'm saying not like your practical labs, okay? Sorry, I mean, practical labs are very important because you learn all sorts of experimental skills, but let's not confuse it with experimental physics. Now, yesterday, we talked about the stress tensor, okay? And, it's actually kind of hard to visualize. Maybe it's a little bit easy. I mean, it is something that engineers do a lot of. They play with stress tensors a lot. And one of the reasons for that is because of things like this. This is actually tunneling through a mountain in China. It's actually water tunnels, but it also just happens that in one of these water tunnels, they stuck an underground physics lab, okay? And it's a very deep underground physics lab. It's actually, I mean, by certain measures, it's actually the deepest underground physics lab in the world. But in drilling these kinds of tunnels, you get these rock faces, and they're also, and basically they are cutting away rock. So whenever you cut away rock, you have all sorts of strains and things like that are kind of left over, and now there's no other rock that's actually supporting it. And so if you kind of don't do it carefully, you get these things called rock bursts where, your walls tend to collapse. Yeah. Now, that does have a little bit of an effect when you actually have to do your physics underground. So this is now Snow Lab, which is just a little bit shallower than the Chinese lab. But actually, the characteristics are quite different. Snow Lab is actually sitting underneath a flat terrain. It's actually quite boring terrain, whereas the Jinping laboratory is actually underneath a mountain. So, cosmic radiation can come from shallower angles. Anyway, yeah, so this is actually again, one of the deepest labs, one of the deepest underground physics labs. And for now, I'm just going to say, well, look, isn't it cool that we do this? And of course, I also have to have this little picture in here because otherwise you'll never believe me, right? Yeah, I had to go through all the sort of mine safety training, sitting there with young miners as well as my graduate students, learning about how to turn on the electrical power equipment without burning yourself, all this other kind of stuff. And because of things like rock bursts, you get things like all this metal netting around, right? That's one thing. This is actually on the walk to the lab. You kind of suit up in all this stuff, and then you sort of, you take an elevator that goes straight down, and then you walk for about 45 minutes to get to the entrance of the lab itself. Once you get into the lab, you kind of sit in this little place, and you have your second breakfast, actually, because you do it really early in the morning. And yeah, so while they're actually checking to make sure that the mine air is safe to breathe, they have safety officers going around. All you can do is kind of like just have breakfast again. Yeah, that's what these guys are doing. The other use of this is that this is also the refuge. So if there is a rock burst, they will tell you get back to the refuge because this is kind of with hardened walls, and they're pretty sure that this one's not going to collapse, even though something else might. Okay. because actually SNOLAB is situated in an active mine. Just for admiration, I just like these pictures. This is actually the Snow Plus detector. Those are people down there, I think. Yeah, so this is kind of big. Those are photomultiplier tubes. I'll show more pictures of it some other time. This is kind of from the early days of snow, so the different mining equipment. That's Art McDonald. He's the one who got the Nobel Prize for the snow experiment some years ago. And then this is actually what the collaboration looked like at least a couple of years ago. There's Art now. Still comes to our meetings, and this gives the impression of lots and lots of really happy people working on an experiment together. But actually, yeah, all of these people, or almost all of these people, do suit up, go underground, and get all the training for dealing with things like rock bursts. Okay, so let's see. Did I have anything else for? Yeah, we'll just leave that friendly picture up there. It is great working with these people, got to say. So don't mind having a picture with lots of smiling faces on it. Okay, so yeah, experimental physics. I think tomorrow I'll probably go a little bit more into that because we'll still be in group theory. So you got to have a little bit of sort of you might say therapy. Okay, right. Now we're going to now pick up your pens again. We're going to continue with SO2. Right, let's see. Okay, so now we had just talked about the generator. Now the generator, when you look at it, this is actually the whole thing about a generator is that you're looking at sort of n element in your state space, and then you're looking at just the next element. Okay, now it just happens to be infinitely close, but it is kind of like the next element over. There are a couple, and actually in the theory of Lie groups, a lot of the algebra of the group is actually found in the generator. Okay, but not all of it, and we'll see a little bit more of that later. But not all of that will be in the generator itself, because this is only what we would call the sort of local behavior. Okay, because this is an element and its neighbor. Certain other things are not in the generator. And that we can call sort of, global behavior. So can you think of one little important bit of global behavior which you would not find in an infinitesimal rotation? Sorry? Periodicity. Yeah, something like that. Okay. In particular, that thing about let's see, phi plus 2 pi. Okay. Right. The fact that if you go around, a finite angle of 2 pi and you end up at the same group element, okay, that is not to be found in the generator. So this has to be something that gets imposed from the outside. Okay, now keeping that in mind, now we can talk about representations. Now, I'm going to pull a little sleight of hand here. We were going to talk about the representations of SO2, but remember that SO2 is just sort of, rotation around the, around an axis. So actually, another thing that, another sort of way of thinking about the elements of this group is position. So if you think about sort of like position on a unit circle in complex space. Okay? So Yeah, because I mean the distance doesn't actually matter. It's just it's really just the angle that we're looking at. So in fact, we already get that you know, we can pretty much use the U1 group. Okay, so 1-by-1 unitary matrices as a representation of SO2. Okay, there is in fact an isomorphism between the two. Okay. Okay, but using that, now let's start picking apart the structure. So let UM phi equal e to the minus I m phi. Okay, so that's a statement, so let's just pick out some values of m and see what happens. So if m is equal to 0, right, okay, actually it should be just a little bit clearer. Well, no, let's go with this. So m equals 0, this guy is the one where everything just maps to the identity element, right? So, yeah, this is the trivial representation. Okay, now m is equal to 1. This is where, you know, you have r of phi corresponding to u1 phi is equal to e to the minus I phi, okay? So here we have an isomorphism with SO2. Okay. Yeah. So sometimes this is also called a faithful representation. Okay. Now, this is not the only isomorphism, however, because if m is equal to minus 1, right, you get the same kind of thing. It's just u1, u minus 1 phi is equal to e to the I phi. So similarly isomorphic. Okay, but instead of rotating in one direction, it's simply rotating in the other direction. So yeah, you have two faithful representations, and in fact, let's see. If you were to write down, so if you were to write down the generators for the faithful representations, then the generator for the faithful representation, you would actually write J is equal to 1 and minus 1. Actually, we should probably get into that just a little bit later on. So don't worry about that just this second. We'll talk about the generator bases when we get to 3D rotations. Okay. In the meantime, let's just talk about some other representations. If you had m is equal to plus or minus 2, okay. So in this case, so you know you have e minus or plus or minus I 2 phi. Okay. So in this case, now you only have to instead of going from, you know, phi is equal to 2 pi, giving you the same element again, now if you just rotate through pi, you get the same element. Okay? So in this case, you can kind of say that, you know, this is clearly not a one-to-one correspondence, but the representation, let's see, one element in this representation corresponds to two elements in SO2. Okay, so an example of a homomorphism, but the multiplication rule still holds. Yeah. Now, that's great for integers, and you can kind of keep on doing this, right? You would actually have things that, I mean, you know, sort of like when you think about what the meaning of the representation actually is, You can think of it this way, or use a sort of physical example, right? Here's your unit circle, and let's say you had a number of waves on this unit circle. Okay, well, that's not great, but you know, the thing is that if you have an integer number of waves, then you can actually sort of divide this up. I wish I drew this a little bit better. That's horrible. Anyway, let's say we had 3 waves. That means that actually every 120 degrees, this is the same wave function. Okay? So, you know, you rotate only by 120 degrees, you're actually in an m plus or minus 3 representation. And yeah, it leaves the system unchanged. Now, that's not the only, I mean, that's great for m is equal to an integer, but there is also, you can also set m is equal to plus or minus 1/2. Now this, in this particular case, this means you have to rotate through 4 pi to get to the identity. Okay, or get back to the same element. Okay. So this is sometimes called a double-valued representation, in the sense that now we have 2 elements in the representation corresponding to 1 element in SO2. Okay, so this is kind of like, you know, the opposite of that case where you have one element corresponding to 2. Now we have 2 elements corresponding to 1. Still have the same periodicity, still have the same multiplication rule. It is a perfectly legitimate representation. And in fact, gets even worse than that because it turns out that you can have, you know, a representation mn, which basically is e to the minus I m phi over n. And so as long as m and n are mutually prime, okay, in other words, don't have any common factors, this is also a representation of SO2. Okay? Right. Okay. Now, I think what I've done is that I've just sort of, I mean, and what it'll probably feel like is that I've just given you kind of a shotgun blast of definitions, okay, and just illustrations of how those, of what those definitions mean. I think it'll become a little bit easier to understand, or easier to see why we're doing this when we start talking about the 3-dimensional rotations, because the structures will get a bit more involved than this, and we'll also see what the use of those representations are. But I think this is actually, you know, kind of close to the end. So, any questions on the sort of basic representation theory? Okay. Question? Yeah.
Does the permutation group get a sort of symbolic linear way than
Probably. I think actually, yeah, in fact, I think what you'll see is the permutation group, it'll be like S3. I don't know why it's S, though. But yeah, sometimes you'll see that. Anything else? Okay, we'll stop right there, and tomorrow we will get back into the 3-dimensional world.